The morning of January 12, 1943, inside factory number 183 in Nizhny Tagil, a welder named Klavdia Kozyreva watched her hand tremble as she struck an arc. The electrode hissed against cold steel, throwing sparks across the concrete floor of the massive tank assembly hall. She had been welding 34 hulls for 11 hours straight, and her supervisor had just informed her that the daily quota had been increased again. 40 tank hulls per shift. The Germans were pushing towards Stalingrad, and every hour of delay meant more Soviet soldiers facing panzers with nothing but rifles and grenades. But Kozyreva's trembling hand wasn't from exhaustion. It was from something she'd witnessed 30 minutes earlier in the experimental welding section, where a twande of engineers had just demonstrated a technique so radical, so seemingly impossible, that it violated everything she'd been taught about joining armoured steel. A technique that would, within 6 months, allow Soviet factories to produce tanks faster than German forces could destroy them. A technique that would turn the tide of industrial warfare and reveal a truth the Wehrmacht had refused to believe: that the Soviets possessed not just numerical superiority, but technological innovation that German engineers had dismissed as impossible. The innovation was called automatic welding under flux, and the man who invented it, Dr. Yevgeny Oskarovich Patton, had just solved a problem that had plagued every tank-producing nation since armoured warfare began. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why Patton's invention represented such a revolutionary breakthrough, you need to understand the bottleneck strangling Soviet tank production in 1942. The 34 medium tank, with its sloped armour and powerful 76mm gun, was already proving itself superior to most German armour on the battlefield. Soviet designers had created an excellent weapon. But creating the design was the easy part. Manufacturing it in quantities sufficient to replace combat losses was another matter entirely. Every 34 hull required approximately 150 metres of welded seams. In 1942, every centimetre of those seams had to be laid by hand, by a skilled welder using manual arc welding techniques. The welder held an electrode holder, maintained the correct arc length, controlled the travel speed, and ensured proper penetration, all while working with a high-carbon armour plate that cracked if the heat input wasn't precisely controlled. A skilled welder could complete perhaps 8 to 10 metres of acceptable armour-grade welds per hour. This meant each hull required approximately 15 to 18 hours of welding time, not counting setup, positioning, and inspection. And this assumed you had skilled welders. The Soviet Union, in the chaos of 1942, did not have nearly enough skilled welders. The best welders had been conscripted into the Red Army. The factories had been evacuated from Ukraine and Western Russia to the Urals, leaving behind experienced workers. The people now staffing the tank factories were often women with minimal training, elderly men past military age, and teenagers barely strong enough to hold the welding equipment. Factory number 183 in Nizhny Tagil faced a crisis that crystallized the entire Soviet industrial dilemma. In December 1942, the factory received orders to increase monthly 34 production from 180 tanks to 300 tanks. But they didn't have 300 welders capable of producing armour-grade seams. They barely had enough welders for current production levels. And training new welders to the required skill level took 6 months to a year. The mathematics was brutal. If each tank required 18 hours of welding time, and each welder could work effectively for only 8 hours per day, then each hull needed 2¼ days of welder time. To produce 300 tanks per month meant completing 10 tanks per day, which required 22½ days of welding work per day, which meant the factory needed at least 23 welders working simultaneously on hull seams alone. But the quality requirements were so strict that newly trained welders produced rejection rates of 30 to 40%. Their welds cracked under ballistic testing. Their penetration was inconsistent. Their slag inclusions created weak points where an 88mm round could fracture the armour. The Soviet solution to most wartime production problems was brute force. Throw more workers at the problem, extend the shifts, accept lower quality. But you couldn't brute force armor welding. Bad welds meant dead tank crews and destroyed vehicles. The Red Army had learned this lesson harshly in 1941, when hastily welded tanks shattered along their seams under German fire. Dr. Yevgeny Paton understood this bottleneck intimately. At 54 years old in 1942, he was already one of the Soviet Union's most respected welding engineers, director of the Electric Welding Institute in Kiev. He had spent 2 decades studying metallurgy and welding processes. But when the Germans invaded in June 1941, Paton's institute was evacuated east, first to Ufa, then to Nizhny Tagil, where it was embedded directly inside factory number 183. Paton had been thinking about automated welding for years, but the war transformed it from academic curiosity into desperate necessity. The concept was theoretically simple. Replace the human welder with a machine that could maintain perfect arc length, perfect travel speed, perfect electrode angle. But the practical challenges were immense. How do you protect the weld pool from atmospheric contamination without a human continuously adjusting a shielding gas flow? How do you prevent the automatic system from creating exactly the kind of slag inclusions and porosity that made manual welding so difficult? Paton's solution was elegantly simple in concept, ferociously difficult in execution. Instead of using shielding gas or a flux coating on the electrode, he would bury the entire welding arc under a layer of granulated flux powder. The electrode would feed automatically into this flux layer, creating the arc beneath the powder. The flux would melt from the arc heat, creating a protective slag layer over the weld pool, shielding it from oxygen and nitrogen in the atmosphere. The welding head would travel along the seam automatically, maintaining perfect parameters, while the unmelted flux powder could be vacuumed up and reused. The theoretical advantages were staggering. An automatic welding head could maintain a travel speed 3 to 4 times faster than a human welder. It never got tired, never lost concentration, never needed breaks. It could weld continuously for hours, limited only by the supply of electrode wire and flux powder. And most importantly, it required almost no skill to operate. A worker with just a few days of training could set up the automatic head, start the process, and monitor it, freeing up the few remaining skilled welders for complex joints that still required human judgment. But theory and practice, as Paton knew, were separated by countless potential failures. The flux chemistry had to be precisely formulated. Too much of certain minerals, and the slag wouldn't release cleanly. Too little, and the weld pool would be contaminated. The electrode feed rate had to match the burn-off rate exactly, or the arc would extinguish. The travel speed had to be calibrated for different thicknesses of armor plate. The amperage and voltage had to be controlled within tight parameters. Paton's team began experiments in late 1941, working in cramped quarters with improvised equipment and whatever materials they could scavenge from the factory stores. They tested dozens of flux compositions, trying to find the formula that would produce clean, strong welds without trapping gas bubbles or creating brittle microstructures in the heat-affected zone. They built crude automatic welding heads from scrap motors and gearing, trying to achieve smooth, consistent travel speeds. By March 1942, they had achieved their first successful automatic welds on thick armor plate. The seams looked different from manual welds wider, with a distinctive rippled appearance from the automatic travel, but the metallurgical testing showed they were actually superior. The heat-affected zone was narrower because of the faster travel speed. The penetration was more consistent because the arc length never varied. And most surprisingly, the quality was so consistent that the rejection rate dropped from 30% to less than 5%. In April 1942, Paton received permission to install the first experimental automatic welding setup on factory number 183's production line. The installation was crude by later standards. A welding head mounted on a simple track system, hand-adjusted for each seam. But when they ran the first production test on a 34 hulls bottom plate welding the seam between the side panel and the floor, the results were undeniable. The automatic head completed the seam in 42 minutes. A skilled manual welder needed 3 to 4 hours for the same seam. The automatic weld passed all ballistic and metallurgical tests on the first try. A manual welder averaged a 30% first-time pass rate on that particular seam because of the awkward angle and the length of continuous welding required. But the most important result wasn't visible in the numbers. It was visible in Klavdia Kozireva's face when she watched the automatic headwork. She had been welding that exact seam by hand for 8 months. She had burned through countless electrodes, endured the physical strain of maintaining the correct angle for hours, felt the frustration every time an X-ray inspection revealed a defect that meant starting over. And now she was watching a machine do in 42 minutes what took her 4 hours, and do it better than she could on her best day. The German intelligence analysts, reading reports of Soviet tank production increases through late 1942, assumed the Soviets were simply throwing more workers at the problem, accepting lower quality, cutting corners. German welding remained entirely manual throughout the war, performed by highly skilled craftsmen who took pride in their smooth, aesthetically perfect seams. German tank factories assigned individual welders to specific seams on Tiger and Panther hulls, treating each vehicle as a crafted product. The Germans assumed, as they had assumed about so many aspects of Soviet capability, that Russian industrial methods were primitive, that Soviet quality control was non-existent, that increases in quantity necessarily meant decreases in quality. They were wrong on every count. The Soviets weren't lowering their standards. They were revolutionizing the entire process of armored vehicle production, and they were doing it with a level of technological sophistication that German industry wouldn't match until after the war ended. By June 1942, Factory number 183 had installed automatic welding equipment on 6 different seam types. By September, that number had grown to 14. Each installation required custom engineering, designing the track systems, calibrating the parameters for that specific joint, training operators, modifying the assembly sequence. But each installation removed another bottleneck from production. The results showed up in the monthly production reports with mathematical clarity. In January 1942, Factory number 183 produced 147, 34 tanks. In July 1942, with 6 automatic welding stations operational, production reached 212 tanks. By December 1942, with 14 stations operating, the factory produced 318 tanks. This was not a gradual improvement. This was a step function increase in industrial capacity, achieved with essentially the same number of workers, in the same facility, with the same raw material supplies. The quality improvements were equally dramatic, but took longer for frontline units to recognize. Tank crews in 1941 had learned to distrust hastily welded vehicles. A 34 with poor welds could split its hull seams under the stress of rough terrain or the shock of near-miss artillery. Commanders learned to inspect the welds on newly delivered vehicles, looking for the telltale signs of rushed work, incomplete penetration, excessive spatter, visible undercut. But the 34s rolling out of factory number 183 in late 1942 displayed welds that confused experienced crews. The seams were wider than traditional manual welds, with a distinctive scaly appearance that suggested machine work, yet the penetration was deeper than manual welds typically achieved. The slag cleaned off easily, revealing smooth, consistent bead patterns. And when these tanks went into combat, they didn't fail along their seams. The armor cracked or deformed under direct hits, as it always had, but the welded joints held. The tanks that limped back from the battlefield with battle damage showed fractures in the base metal, not weld failures. People's Commissar of Tank Production Isaac Zaltzman recognized the implications immediately. On August 27, 1942, he issued Order Number 571, mandating that all tank production factories in the Soviet Union begin immediate transition to automatic welding. The order listed specific seams that were to be converted first: the seam between the hull side and the sponson floor, the seams connecting the cross beams to the upper and lower front plates, the turret ring connection points. The resistance Zaltzman encountered was immediate and predictable. Factory directors protested that they lacked the equipment, the electrical capacity, and the trained engineers. Some argued that automatic welding was unproven, risky, a dangerous experiment that would compromise quality exactly when the Red Army needed reliable vehicles most desperately. Others insisted that their workers were already skilled enough, that traditional methods were sufficient, that the disruption of installing new equipment would actually decrease production in the short term. Salzman overruled every objection. He understood what the factory directors did not, that the Soviet Union was locked in a race between industrial capacity and catastrophic military defeat. The Germans had reached the Volga River at Stalingrad. They were pushing toward the Caucasus oil fields. Every projection showed that if current loss rates continued, the Red Army would run out of tanks before the Germans ran out of panzers, regardless of how many 34s the factories produced, because they couldn't produce them fast enough. The transition was brutal. Factory number 112 in Gorky, which had been producing KV-1 heavy tanks using entirely manual welding, received its first automatic welding equipment in October 1942. The installation disrupted production so severely that November output dropped by 18%. Workers who had spent years perfecting manual welding techniques resented being reassigned to monitor machines. The first automatic welds at Gorky failed inspection at a 40% rate because the flux chemistry hadn't been properly calibrated for the thicker armor of the KV-1. But by January 1943, Gorky's automatic welding stations were operational and properly calibrated. By March, production had increased 23% over the pre-automation baseline. By May, 41% of all welds on KV-1 hulls were being performed automatically, and the rejection rate had dropped to 3%. The pattern repeated across the Soviet tank industry. Uralmash Factory. Factory number 174. Factory number 176. Each struggled through the transition. Each initially saw production drops and quality problems, and each emerged producing more tanks, faster, with fewer defects. The learning curve was steep, but the Soviets had one advantage that German industry lacked. They were willing to accept short-term chaos in pursuit of long-term capacity increases. Dr. Patton's team, meanwhile, continued refining the technology. The original automatic welding heads were crude, requiring manual positioning for each seam. By mid-1943, Patton's Institute had developed semi-portable units that could be moved along the hull and locked into position with quick-release clamps. The flux formulation was improved to reduce fume generation and allow faster travel speeds. The electrode wire, initially imported from the United States under Lend-Lease, was redesigned so Soviet mills could produce it domestically. Each improvement rippled through the entire production system. When travel speeds increased from 12 centimeters per minute to 18 centimeters per minute, welding time per hull dropped by another 33%. When the flux chemistry was improved to permit single-pass welding on plates up to 25 millimeters thick, entire welding operations could be eliminated. When portable units replaced fixed installations, the same equipment could be used on multiple seam types, reducing the capital investment required. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Germans, monitoring Soviet tank production through intelligence reports and interrogation of captured workers, fundamentally misunderstood what they were observing. German analysts saw the production increases and assumed the Soviets were sacrificing quality for quantity. They saw reports of machine welding and assumed it meant lower skilled work and inferior results. They saw photographs of 34 welds with the distinctive scaly appearance of automatic welding and classified them as evidence of crude manufacturing techniques. This misunderstanding was rooted in German industrial philosophy. German tank production emphasized craftsmanship, precision, and individual skill. A Tiger tank hull was welded by master craftsmen who had trained for years. The welds were aesthetically perfect, smooth, even, with no visible defects. Each Tiger was, in a sense, a work of precision engineering, assembled with the care of a luxury automobile. German engineers assumed that manufacturing quality required human skill at every stage. The idea that a machine could produce superior welds seemed to contradict the fundamental principles of their industrial system. When German technical intelligence officers examined, captured 34 tanks in late 1942 and early 1943, they noted the machine-welded seams, but interpreted them as evidence that the Soviets were using less skilled workers and accepting lower standards. The reality was exactly the opposite. The automatic welding wasn't a compromise forced by lack of skill. It was a technological leap forward that German industry, for all its vaunted engineering excellence, had failed to achieve. The Soviet welds weren't inferior to German manual welds, they were superior in almost every measurable way. More consistent penetration, narrower heat-affected zones, lower defect rates, faster production times. And, most importantly, they could be produced by workers with minimal training, which meant the Soviets could staff their factories with whoever was available, while their skilled workers served in combat units. The German misperception created a strategic blind spot that persisted throughout the war. When German commanders requested more Tigers and Panthers to counter increasing numbers of Soviet tanks, German industrial planners assumed the problem was one of design, that German tanks needed to be qualitatively superior to offset Soviet numerical advantages. They never grasped that the Soviets had achieved both quantity and quality by fundamentally rethinking the manufacturing process. By mid-1943, the transformation of Soviet tank production was complete in its essential outline. Approximately 60 to 75% of all welds on 34 hulls were being performed automatically. Some specialized joints still required manual welding, complex curves, dissimilar metal joins, repair welds, but the bulk of production welding had been mechanized. The Soviet Union was producing approximately 1,034 tanks per month, more than triple the production rate of 18 months earlier, with essentially the same industrial workforce and facilities. But the full impact of Patton's innovation became clear only when German forces encountered the results on the battlefield. The summer offensive of 1943, Operation Citadel, was designed to destroy Soviet armored reserves in a massive encirclement at Kursk. German planners anticipated that Soviet tank forces, despite their numbers, would be vulnerable because of inferior quality. Intelligence estimates suggested that Soviet tanks would suffer high mechanical failure rates under sustained combat operations, that their armor welds would crack under stress, that rapid production had necessarily compromised reliability. The Battle of Kursk shattered every one of these assumptions. When the German offensive began on July 5, 1943, they ran into Soviet armored defenses unlike anything they'd encountered before. The 34s weren't just numerous, they were mechanically reliable, with hull welds that held up under the most brutal combat conditions. German after-action reports noted with surprise that Soviet tanks destroyed in combat almost never showed weld failures. The hulls cracked, the turrets were blown off, the suspensions were destroyed, but the basic welded structure held together. Lieutenant Hans Becker of the 5th SS Panzer Division Weaking recorded his observations after 3 weeks of combat at Kursk. "We destroyed perhaps 30 Russian tanks in the fighting around Prokhorovka. I personally inspected 5 of the wrecks afterward. Every one had suffered catastrophic internal fires or ammunition explosions, but the hull structure remained intact. The welds showed no signs of failure. This is very different from the Russian tanks we fought in 1941, which sometimes split their seams simply from the shock of hits that didn't penetrate. These newer tanks are much better constructed, though our intelligence insists Russian quality is declining." Becker's observation captured the cognitive dissonance that German field commanders experienced throughout the last 2 years of the war. The evidence before their eyes contradicted the intelligence assessments they received. Soviet tanks performed better than expected, not worse. Soviet manufacturing quality improved over time, not degraded. And Soviet production increased continuously, despite the most optimistic German predictions that Soviet industry would collapse under sustained strategic bombing and resource shortages. The disconnect between German perception and Soviet reality extended beyond tank hulls to the entire Soviet industrial system. German planners believed that Soviet factories were primitive, that Soviet workers were poorly trained, that Soviet engineering was derivative of Western designs. These beliefs were comforting because they implied that German industrial superiority would eventually triumph regardless of Soviet numerical advantages. But the truth was that the Soviet Union had, by necessity, innovated in ways that German industry hadn't needed to consider. Automatic welding was just one example. The Soviets had also pioneered automated machining for engine blocks, stamped armor construction for certain vehicle types, and simplified assembly sequences that reduced production time. Not because Soviet engineers were more brilliant than German engineers, but because Soviet circumstances demanded innovation or defeat. The women workers in the Soviet tank factories understood this in a way that German intelligence analysts never could. Klavdia Kozyreva, who had watched the first automatic welding demonstration in January 1943 with a mixture of fear and wonder, spent the remainder of the war training other women to operate the automatic welding equipment at factory number 183. She became an expert in flux chemistry, learning to adjust the composition based on ambient temperature and humidity. She trained hundreds of workers, most of them women under 25 or men over 50, teaching them to set up the equipment, monitor the process, and identify the subtle signs of incorrect parameters. In her post-war memoir, published in 1968, Kozyreva reflected on the transformation. "We were told by our supervisors that the fascists believed we were incapable of producing quality weapons, that we were inferior workers using inferior methods. But I had seen the German tanks we captured. I had seen their welds. They were beautiful, smooth, perfect to look at. Ours were rougher, scaled, obviously made by machine. But ours were stronger. Our tanks came back from battle with terrible damage, but the welds held." The German assumption that beauty meant quality, that machine work was inferior to handwork, was their mistake. And we exploited that mistake every day, every shift, producing 3 tanks where they produced 1. The German failure to adopt automatic welding had multiple causes. Part of it was institutional. The German industrial system was built around skilled craft workers and master-apprentice relationships. Replacing skilled welders with machines threatened the entire social structure of German manufacturing. Part of it was ideological. National Socialist rhetoric emphasized German craftsmanship and individual excellence over mass production, and part of it was simply lack of necessity. Germany never faced the absolute shortage of skilled labor that forced Soviet innovation. But regardless of cause, the result was that German tank production remained fundamentally manual throughout the war. A Panther tank hull required approximately 100 to 60 hours of welding time, all performed by hand. A Tiger II required over 200 hours. Each vehicle was welded by master craftsmen who treated their work as skilled artistry. The welds were perfect. The production rates were inadequate. Germany produced approximately 6,000 Panther tanks during the entire war. The Soviet Union produced over 40,034 tanks during the same period, many of them with armor and gun combinations that could defeat the Panther frontally at combat ranges. The Panther was, in many ways, a superior tank, better optics, better gun, better armor protection. But the Soviets could lose 5 34s for every Panther and still have reserves to continue the offensive. And increasingly, they didn't need to accept those loss ratios because the 34s were well-built machines with reliable hull welds that kept fighting even after sustaining damage that would have mission-killed earlier. Models. The strategic implications became undeniable by 1944. When Soviet forces launched Operation Bagration in June 1944, they assembled over 5,400 tanks and self-propelled guns for the offensive. The German forces opposing them had approximately 900 operational armored vehicles. The numerical disparity was so overwhelming that German commanders couldn't concentrate enough force to stop any single breakthrough, and Soviet doctrine didn't require stopping, they simply bypassed German strongpoints and continued advancing. German after-action reports from Bagration repeatedly noted that destroyed Soviet tanks appeared to be recent production, with fresh paint and minimal mechanical wear. The implication was clear. Soviet industrial production was accelerating even as German production struggled to replace losses, and the quality of Soviet vehicles was sufficient for their operational requirements. They didn't need Tigers that could survive 10 direct hits. They needed 34s that could survive the drive to the battlefield, engage German positions effectively, and be produced in sufficient numbers that losses were replaceable. Dr. Peyton never visited the front lines during the war. He remained in Nizhny Tagil, continuing to refine automatic welding technology, developing new applications, and training engineers from other factories. But he understood what his invention had achieved. In December 1943, he received the Stalin Prize First Class for his contributions to Soviet industrial production. The award citation specifically mentioned that his automatic welding technology had increased tank production efficiency by a factor of 10 while simultaneously improving quality. That factor of 10 was not hyperbole. In the specific application of long, straight seams on flat or slightly curved armor plate, automatic welding was genuinely 10 times faster than manual welding by a skilled operator, and perhaps 20 to 30 times faster than manual welding by a newly trained operator. When you aggregated those improvements across an entire tank hull, across hundreds of tanks per month, across dozens of factories, the cumulative effect was transformative. The human cost of this transformation is harder to quantify, but no less significant. The women and elderly men and teenagers who staffed Soviet tank factories in 1942 faced brutal working conditions, 12 to 16-hour shifts, minimal food rations, unheated facilities in the Ural winter, constant pressure to increase production. Welding by hand under those conditions was physically punishing work. The introduction of automatic welding didn't eliminate the hardship, but it did reduce the most physically demanding and skill-intensive tasks to machine operation that required attentiveness rather than strength and precision. Klavdia Kozyreva's daughter, interviewed in 1998 for a documentary on Soviet wartime industry, recalled her mother's descriptions of the factory. She said that before the automatic welding, the women welders would come home and their hands would shake so badly they couldn't hold a fork. The strain of maintaining the exact arc distance for hours, the heat, the fumes, the constant concentration, it destroyed women physically. After the automatic machines, the work was still hard, still dangerous, still exhausting. But it was different. You were monitoring the machine rather than being the machine. She said it was the difference between impossible and merely terrible. The Soviet Union never publicized the details of automatic welding during the war. It was classified technology, considered militarily significant. When American engineers visited Soviet factories under Lend-Lease arrangements, they were shown certain production areas but carefully kept away from the automatic welding stations. Soviet technical publications mentioned improvements in welding efficiency, but didn't specify methods or equipment. The assumption was that any significant technological advantage should be preserved as long as possible. Ironically, American industry had developed similar automatic welding technologies independently, most notably for Liberty ship production. The Americans called it submerged arc welding and used it extensively for ship hulls starting in 1942. But the American and Soviet innovations occurred in parallel, without knowledge of each other's work, driven by similar pressures. The need to produce welded structures faster than skilled welders could work manually, using whatever labor force was available. The Germans learned about Soviet automatic welding only after the war, when Allied technical intelligence teams examined, captured Soviet factories and interviewed Soviet engineers. A 1946 British intelligence report on Soviet tank production technology noted with surprise that the Soviets achieved welding automation in armored vehicle production before Germany, Britain, or the United States. This automation was a significant factor in the Soviet ability to maintain high production rates despite severe skilled labor shortages. German intelligence during the war consistently underestimated Soviet manufacturing capabilities, apparently assuming that Russian industry was primitive rather than innovative. That German underestimation had strategic consequences that extended far beyond welding technology. The entire German operational approach on the Eastern Front, assumed that Soviet industrial capacity would eventually collapse, that Soviet armies would run out of equipment, that numerical superiority would erode over time as losses exceeded production. These assumptions were built on a fundamental misreading of Soviet industrial capabilities and, more specifically, on the German failure to recognize that desperate necessity had driven Soviet innovation in directions that German industry hadn't considered. The Battle of Berlin in April and May 1945 crystallized the ultimate irony. German defenders fought with whatever weapons remained available, including a small number of Tiger II tanks, each one a masterpiece of precision engineering, each hull welded by master craftsmen over hundreds of hours. The Soviet forces attacking them included thousands of 34-85s and IS-2 heavy tanks, many of them with hulls welded by women operators using automatic equipment, produced in a fraction of the time required for German vehicles. The German tanks were, in isolation, superior machines, better armor protection, better guns, better optics. But there were dozens of Soviet tanks for every German tank, and the Soviet tanks were reliable enough, well built enough, mechanically sound enough to do their job. The welds held, the engines ran, the guns fired, and there were always more of them. Lieutenant Hans Becker, the same officer who had noted the surprising quality of Soviet tank construction at Kursk in 1943, survived the war and was interviewed in 1961 about his experiences. Asked about Soviet tanks, he said, "We were taught that German engineering was the best in the world, that German workers were superior, that German method produced superior results. And in a narrow technical sense, that was true. Our tanks were engineered to finer tolerances. Our welds were more beautiful. But the Russians understood something we didn't, that the best tank is the one that exists in sufficient numbers to win the battle. They built crude-looking tanks with machine welds and stamped parts, and they built them by the thousand. And those crude-looking tanks beat us. That was the hardest lesson to learn, that all our precision and craftsmanship meant nothing when we were outnumbered 5-1 by tanks that worked well enough to kill us." Dr. Peyton continued his work after the war, founding the E.O. Peyton Electric Welding Institute in Kiev, which became one of the world's leading research centers for welding technology. He died in 1953 at age 65, having lived to see automatic welding become standard practice in industries worldwide. His wartime innovation had been adopted by American, British, French, and eventually even German manufacturers in the post-war period. The technique he developed under desperate wartime conditions became the foundation for modern automated welding in everything from pipelines to ships to buildings to automobiles. But Peyton's most significant achievement wasn't the technical innovation itself. It was demonstrating that industrial warfare could be won not just by superior weapons but by superior manufacturing processes. The German assumption that craftsmanship meant quality, that machine work was inferior, that traditional methods were always best. These assumptions were comfortable because they validated existing systems. But they were wrong. And the cost of that wrongness was measured in German tanks destroyed, German offensives halted, and ultimately German defeat. Klavdia Kozieva worked at factory number 183 until she retired in 1968. She trained hundreds of welding operators, most of them women, teaching them to use equipment that became progressively more sophisticated as Soviet industry rebuilt and modernized after the war. In her final interview before her death in 1982, she was asked what she was most proud of from her war service. She said, "I am proud that we built tanks faster than the fascists could destroy them. We took girls from farms who had never seen a welding torch, and we taught them to operate machines that produced work better than the German master welders. That we proved you don't win wars with the most beautiful tanks. You win wars with enough tanks that work well enough. The Germans thought we were primitive. They thought our methods were crude. And while they thought that, we buried them in 34s with machine welds that held up to anything they could throw at us. That is what I am proud of." The final production numbers tell the story with unambiguous clarity. From January 1942 to May 1945, Soviet factories produced approximately 58,000 medium and heavy tanks, the overwhelming majority of them using automatic welding for the majority of hull seams. German factories produced approximately 24,000 medium and heavy tanks during the same period, all of them using manual welding throughout. The Soviet tanks had, on average, lower manufacturing costs, shorter production times, and comparable or better weld quality than the German tanks. They were not inferior products made by inferior methods. They were the result of industrial innovation driven by necessity. The profound historical irony is that the Germans, who prided themselves on engineering excellence and technical superiority, lost the industrial production war to an enemy they considered technologically primitive. The Soviets, facing catastrophic labor shortages and industrial disruption, innovated their way to production levels that German industry couldn't match. And they did it not by copying German methods, but by developing fundamentally different approaches that German engineers had dismissed as impossible or unworthy. Automatic welding under flux was just one innovation among many, but it was emblematic of the entire Soviet approach to wartime production. Identify the bottleneck, eliminate human limitations wherever possible, accept short-term disruption for long-term capacity gains, and measure success by output rather than aesthetics. The Germans built beautiful tanks slowly. The Soviets built functional tanks quickly. In the end, quick and functional defeats are slow and beautiful, because wars are won by the side that can replace its losses faster than the enemy can inflict them. The 34 tanks, with their distinctive scaly machine welds, rolled into Berlin in May 1945, their hulls still holding together after hundreds of kilometers of combat operations, proof that Pétain's innovation had worked exactly as intended. The German defenders, firing from their meticulously hand-welded Tiger IIs, were outnumbered and overwhelmed not because of German technological inferiority, but because of German industrial inflexibility. That inflexibility, the inability to recognize that their assumptions about manufacturing were wrong, that machine work could exceed human craftsmanship, that the enemy they considered primitive had innovated beyond them, was perhaps the ultimate German strategic failure. They lost the war in the factories as much as on the battlefields, defeated by welding machines operated by women they would have considered unsuitable for industrial work, producing tanks they considered crude, using methods they considered inferior. History rendered its judgment in May 1945 in the form of thousands of Soviet tanks with automatic welds surrounding the last German strongpoints in Berlin. The Germans had been taught, brutally and definitively, that the best tank is not the one with the most perfect welds. The best tank is the one that exists in sufficient numbers to win. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.